Hi, this video covers our first attempt at a vector-based queue. As we'll see, the vector-based queue turns out to be kind of complicated, and we're going to build up to that in stages. We're going to go through 3 drafts, and you'll see why that is in a moment. So what we're trying to do here is a adapter data structure. Remember that an adapter is a container that uses some pre-existing container to implement a new different interface. What we're trying to do in this video is a vector-based queue. So we're going to try to make a new class that implements a queue using a vector. So we're using the vector data structure to implement the queue operations enqueue, front, and dequeue. The previous video did a linked list based queue. We used a singly linked list to implement the queue. That turned out to be pretty short and sweet and simple. It turns out that the vector based queue is quite a bit more complicated. We'll see why that is. There's lots of moving parts in the final draft of this, and that's because there's 3 problems that need to be solved, 3 practical implementation problems. Rather than present the end of that, which is a pretty complicated data structure all at once that could be confusing, we're going to present 3 drafts, and each one of the drafts is going to solve one of those problems. The final version we get to, it is a little bit complicated, but hopefully it will make more sense when you see where each of these ideas comes from. So here's our first draft. We're going to use a partially filled vector is the idea. So we have a vector data structure, and it stores the elements of the queue. If I have a queue with 7, 1, and 4, and 7 is at the front of the queue, then down here I've got a vector that contains those values, 7, and 1, and 4. There are some other unused elements. We'll get to that in a moment. We have a distinction here between size and capacity. This is similar to the distinction between size and capacity that we had back when we were implementing vector. So remember that vector is a partially filled array. The array object has a certain capacity, which is how many elements it could hold, and then the vector's size is how many elements it actually holds at the moment. We're doing the same kind of thing here, where our queue has a size, which is the number of elements actually in the queue. In my sketch, I've got a 3-element queue, so the size of the queue is 3, but I have a 6-element vector, so the capacity is 6, because this vector object could hold 6 elements, but we're only using 3 of those elements. So we've got size 3, capacity 6 in this sketch. Our queue data structure needs integer variables for front. Front is the index of the first queue element. We'll see in a moment why this is necessary, but the front of the queue is not pinned down at a particular index. It's not like index 0 always holds the front. The front can move. So to keep track of that, we have a integer variable called front, and front tells us where the front element actually is. It's an index number. So if my queue has 714, then in this sketch, front is 2, because 2 is the index number where you can find the 7, the front. And then we also have size that we were just talking about. We need to keep track of that size so that the data structure knows how many elements are there. That's why this sketch says the size is 3. So based on that, we could implement some of these operations pretty simply. The front operation returns the element at the front position of the queue, and we could just simply return vector at index front. That's all there is to it, because this front index is that index where the front element is. Now, to be a good industrial grade implementation, we should have an exception check here. We should say if the queue is empty, throw an exception. I left that out so that this code would fit on the slide. Same thing for dequeue. Dequeue is pretty simple. What dequeue does is it removes the front element. So what do we need to do if we want to take out the front element, which would be the 7? So the 7 goes away and we only contain 1 and 4. Well, what we'll do is just say, forget about this current front element 7. It's not the front anymore. And we can do that by incrementing the front variable. So if front is incremented from 2 to 3, now 3 is the index of 1, 1 is the new front. So that's why we do front plus plus. And then we also need to account for the fact that we removed an element from the queue, so we do size minus minus to keep the size data member accurate. That's all there is to it. Again, there should probably be an exception check there, but we're leaving that out for time right now. Okay, finally, enqueue needs to add an element, and it needs to add an element at the back. So if I look in my sketch here, the back location would be index number 5. It's the index that comes after index number 4, which has the value 4 by coincidence. So the way we could do that is calculate this index, and that index would be the index of the front element plus the size. You know, if you work through the example here, front is 2, and if I add the size of 3, we go 1, 2, 3, and we hop to the first index that comes after the last one that's currently in use. So vector at index front plus size is equal to x. That would store this new x in queued object at index number 5 at the back of the queue. And then we also have to account for the fact that the size increased, so we do size plus plus. Okay, so that's a first draft, and those operations seem like they work. However, there's a problem with them. And the problem is that the partially filled vector can drift out of bounds. So we always want our data structures to keep working indefinitely. People kind of expect it and take it for granted that you can keep doing operations and the data structure will keep working. We don't expect data objects to wear out somehow, but that's what will happen with this draft. In particular, if what we want is that we can do NQ and DQ as long as we want. So that's the way that a queue works. You know, if you think of a line at a grocery store, all day people are going to the back of the line and being removed from the front of the line, and we want that to work. We want to maybe have 1,000 events of add to the front, remove from the back, add to the back, remove from the front. That should work. But the way that this code works right now, eventually that last element will go out of bounds. We have an array out of bounds problem, and I would call this it drifts out of bounds. It's because it kind of gradually moves over to out of bounds. Let's see an example of why that happens, just to be clear about this. So I'm starting with a empty partially filled vector. My front is at index 0. The size is 0 right now. I NQ1, and so what that does is calculate front plus size would be 0 plus 0 makes 0. We add the 1 value at index number 0 of the vector and increment size to 1. Okay, so I NQ'd 1. So far so good. Now if I NQ2, we do the same kind of thing. Front plus size is 0 plus 1 makes 1, so that's why index number 1 will hold value 2. Size gets incremented to 2. We're good. Okay, if I DQ, now what we're going to do is increment front, because 2 is now the front. We're going to decrement size to 1. That's all we do with the DQ. Now if I NQ3, 3 goes at index number 2. I'm going to DQ, the 2 goes away. Now I'm going to NQ4, goes at index number 3. So far so good, no problem yet. I'm going to DQ the 3. Okay, here's where the problem happens. What happens when I try to NQ another element? NQ5. Now, the expectation of a user of our queue is that this should work fine. I've got a queue that only has one element in it. 1 is a tiny number, so it should be able to fit a second element in the queue. The capacity is 4, so I have space for it, but it's not going to work. If I try to NQ5, then we'll calculate the index that we need to store at would be front plus size. That would be 3 plus 1 makes 4. So we're trying to store at index number 4, but that's out of bounds. 4 is not a legal index right now. So this doesn't work. We would get an array out of bounds exception if we tried to run this, and it would crash. So that's the problem. The way the code works right now is this queue can drift out of bounds. As I say, a queue with capacity 4, it should be able to hold 1 or 2 elements, no problem, because capacity is 4. I'm only trying to hold 1 or 2. But the way that this code works, it's not capable of doing that. And NQ and DQ makes the block of used elements drift toward the end. If you kind of notice, here's why I call this drift. This queue is only ever storing 1 or 2 elements. Right now, it's the first 2 that are in use. Then after a DQ and an NQ, now it's the middle 2. See how we're sort of moving to the right? We're migrating rightward. If I do an NQ and a DQ, we kind of move over right one more step. And this is fine until you try to move rightward past the end of the vector, and that's when you get this crash. So these elements are drifting toward the end as they NQ and DQ. And after n of these NQ and DQ operations, if n is the capacity, the queue is drifted out of bounds and it doesn't work anymore. So the next video is going to solve that problem. We're going to see how can we solve this problem so that if you keep alternating NQ and DQ, the queue continues to work, it doesn't drift out of bounds like that.